So in this figure, we see that there are these equipotential surfaces. So what that really means is, let's see, like these surfaces like extend back, right? So these are sheets of equipotential. Right, so they extend back like into the page. And so you have an electron that is going to be moving from this equipotential surface to here and then back. So I'm just going to delete them now, what I've drawn. So if we look at this one, we know that that 80 volts is at a higher potential than 40 volts. So that tells me that this potential right here, if I just look at like this one to this one, this is more positive and this one's more negative because this number is bigger than this number. And so if I have an electron, I know that an electron is not going to want to go over to the negative sheet here because it's negatively charged. So I'm going to have to do work in order to um, bring it this way and then come back. And so in this example, right, same thing. It doesn't want to go this way. And this one, if it goes this way, I'm going to have to do work to push it towards the negative charge surface, and then it'll accelerate towards the positively charged surface because the electron is attracted to the positive surface and it's repelled by the negative surface. So what's the direction of the electric field associated with the surface? Well, I know whenever I have two sheets like this, like right, and one is positive and one is negative, then I know my electric field always points to the right. So it points from positive to negative. So that's all you have to say for that one. Rank the paths according to the work you do moving the electron, greatest first. Okay, so in this case, I'm going to have to do work here. So I'm going to have to do work here. So if I say like 1 for the electron number 1, I'm going to have to do work of, let's see, if I just think like each of these are 10, so I know I'm not going to really calculate numbers. I'm just going to say like this has to go a full 40, or call it even just 4 spots, 1, 2, 3, 4. So I'm going to have plus 4, that's me doing work, and then minus 3, because then I don't have to do work. It's going to be, it's just going to go back to this spot. So minus 3. So I'm going to have a negative 1 or a positive 1 value here. If I think about electron 2, right, I'm going to have to do work of plus 2. And because I'm just going 1, 2 spots, so and I'm going to have to push it because the electron doesn't want to go to the negative surface. And then the third one, I'm going to have to push it 1, so I'm going to have plus 1 and then minus 4 because the electron is going to want on its own to move to the positive charge, so that's going to be equal to negative 3. So the order, greatest first, is going to be 2, and then 1, and then 3. And this should be negative here. So 2, 1, 3 is going to be C. Okay, next. So 2-point charges are separated by a distance 2a as shown. How do we make the electric potential at the origin vanish? We need to place another charge there. So some of the important things about electric potential is that electric potential is a scalar. It's a scalar. We really like that because like electric force and electric field are vectors. So we have to take into account the direction of everything. And that means we have to take into account the components. So we have to do a lot of trigonometry. With electric potential and electric potential energy, we don't. We just can add things up, which is really convenient. So electric potential and electric potential energy are a lot easier to calculate than electric field and electric force. So what do we do here? Well, the electric potential needs to be 0 here. So I'm going to need to put a charge somewhere else because I'm going to have an electric potential due to this one and an electric potential due to that one. So the way I think about it is just one at a time. This negative 2q creates an electric potential that's the same value, whoops, that should go through the origin, that's the same value all along this line of this circle of equipotential, or the sphere of equipotential. So I can calculate what that is. So the potential here is equal to kq over r, and so in our case it's going to be k times negative 2q over a. And notice here, like, I don't really care that I'm at, compared to the origin, I'm at a negative a. I don't have to put in a negative a here, because this formula just tells me the potential at a distance from a charge. So this is the potential at a distance r away from the charge. So I can say that that's a positive value, right? And then for the other one, the positive q, I'm going to have, let's see. So my potential is going to be equal to k. In this case, it's going to be q over a. And so if I want that to be equal to 0, so let's write it up here. If I want v to equal 0, I'm going to have v is equal to a negative 2kq over a from this one, plus kq over a from this one. And now I'm going to have one more. I need another charge so that I can make this equal to 0. So I'm going to just say kq3 over r. I don't know what this is. Okay, so if I add, I can add these two together because I have negative these are the same denominators. This is a negative 2, this is a positive 1. So I'm going to have v is equal to a negative kq over a plus kq3 over r. If I set this equal to 0, then I can solve for q3, right? So I'm going to have q3 is equal to, so let's see, let's bring this over to the other side. So I'm going to have kq3 is equal to kq over a. Cancel out my q's, or my k's, right? And so q3 is equal to, let's see, is equal to r over a. And I can bring this q down over here. So I'm just cross multiplying. So I can have q3 over q is equal to r over a. So in order for this to happen, I need to put a charge at, like if I pick one of these, if I say, I know I want a positive charge, and that makes sense over here because I want something that cancels out one of these negatives, right? So really I just know that I need another kq over a. So I can just say, oh, I know I need a kq over a in order to cancel this out. So that would make sense that my q3 is equal to q and my r is equal to a, right? That would make these two ratios equal. So how do I get that? Well, I need a positive, so that means my b is not viable, my d is not viable. And what about this one? So if I had q3 is equal to 2q, I would need r to equal 2a, not a over 2. So that means I can't use either one of these two because it's going to give me 4 times the amount instead of the same. So the only one left is a, so my answer has got to be a. Okay, next, so I've got, there's a really good video that I shared with you, Joey, on another example where they don't have 3 exact same charges. They have positive charges and a negative charge, and they use a square. So I would go through that one also when you're preparing for your exam. So this is my, for this example, I've got 3 charges. So I'm just going to call them Q, Q, and Q. And it's an equilateral triangle. So I've got, these distances are the same. That makes it really easy. So how much work? So work is, if I think about the formula, is equal to the charge times the potential. And so if I think about like just one charge alone, if I want to bring this Q alone and forget these other two for a minute, if I bring this, I bring it from infinity where potential is equal to 0 to here. And nothing else is around, so there's no work. So to bring the first charge in this group of charges here doesn't doesn't take any work at all. So like for, let's call this one 1, 2, and 3. So work for 1 equals 0. What about work for 2? So work for 2, let's assume 3 isn't there yet. We'll just assume there's just 1 there, and it's held in place. And now I need to bring 2 from infinity to this spot here and then hold that in place. Well, what kind of work do I need to do? So I'll need to do work is equal to Q2 times V1, which is equal to Q because they're the same. And then remember V is equal to KQ over R. And we're going to call these sides of the triangle A, and A. So, so I'm going to have Q, so for Q2, and then K, Q1 over A, which is really just K, Q squared over A. So this is going to be W2, the work to bring this one in. And then what about 3? So now we've got Q1 held there in place and Q2 held there in place. So W3 is going to equal Q3 times the potential of V1 plus V2. So W3 is going to equal Q, because Q3 is just Q, times K, Q over A for 1, plus the same thing, K, Q over A for 2. So the same distance away, same Q's. So, so the work required then to assemble this group of charges is we add them all together, W1, W2, and W3. So we get W total, it doesn't like that, equals 0, plus W1, or W2 is KQ squared over A. And this is 2KQ squared over A. So if I have one of these here from W2 and then W3 is 2, then I can just say this is 3. So W2, or W total, is equal to 3KQ squared over A. And I'm going to let you plug in the numbers here. Just make sure you notice, right? Centimeters is, so when I plug in, let's see, WT is equal to 3 times K. I'm sure you'd have that constant, times Q is going to be 2 times 10 to the minus 6 coulombs, right? Microns are 10 to the minus 6 over A, which is 3 times 10 to the negative 2 meters. And so you can calculate that.